lecture we will discuss about one of the passive island detection techniques, that is the rate of change of superimposed negative sequence based impedance method. Now, before that I will discuss what are the limitations of previously discussed island detection based technique, passive island detection based technique. The first one is the power quality degradation and also complex in nature. The power quality is one of the major issues in case of active island detection based technique, and also in sometimes in if you could see that the rate of change of frequency that we have discussed in the last class, this NDZ, the non detection zone, is one of the major problems. Now, and also we have sometimes uneconomical and due to the variation of the feeder topology or line length or X-Y ratio, some of the techniques are also affected. So, due to different limitations in this particular journey, like in our research laboratory we have discussed or we have developed one technique, and that is basically the rate of change of superimposed negative sequence based technique, and that particular technique we will discuss in this class. Here what we do, the superimposed negative sequence impedance is going to be calculated first. The first step is we have to collect the voltage, 3 phase voltages VA, VB and VC, and also we have to collect 3 phase currents IA, IB, IC at the terminal of the DGs or at the terminal of the DERs. Now, after getting this phases, we are calculating the phases at the terminal of the DERs using least error square based technique, because the least error square based technique can extract the fundamental if the signal is having decaying DC component, and also if the signal is having some harmonic components, then also we can calculate the fundamental component. After getting this, we will just calculate the negative sequence component of the voltage V2, that is basically VA plus A square VB plus A VC, and next we will calculate also I2, that is the negative sequence component of the current, that is IA plus A square IB plus A IC. Here I just want to mention one point, that mostly our distribution network is unbalanced in nature. Due to the presence of single phase loads, unbalancing occurs, and due to that the negative sequence voltage, negative sequence current, both are present even before the disturbance or before the islanding mode of operation. By exploiting this V2 pre information and I2 pre information, we are interested to calculate this Z2 pre, that is known as this negative sequence impedance of the microgrid system at the terminal of the DGs when the system is not disconnected or there is no disturbance present in the microgrid system or smart grid system, that is known as Z2 pre, and this Z2 pre is calculated using this V2 pre divided by this I2 pre. Now, suppose some islanding is there. So, during this islanding mode of operation, again we will also, because it is a continuous process, this islanding relay is mounted at the terminal of the DERs, where continuously we calculate or we measure the voltage and current, and the corresponding phases, negative sequence components of the voltage and current are going to be calculated continuously. Continuously this J2 is going to be calculated at the terminal of the distributed energy resources. Now, when this islanding is there, again also this V2 island or POS I have mentioned here, post after the disturbance V2 POS and I2 POS are also calculated. Using these two quantities, so we will calculate the parameter Z2 POS is equal to V2 POS divided by I2 POS. Now, after getting this, this is the after the disturbance and this is before the disturbance. The difference between these two impedances is known as the superimposed negative sequence impedance. This one you have to understand. What is this superimposed term? What is that superimposed says? The superimposed term, or the definition of the superimposed quantity is that the difference between the post quantity and the previous quantity, pre quantity, or the superimposed parameter means the difference between the post parameter minus the pre parameter. Here this is a superimposed parameter or the impedance. If it is superimposed voltage, so it will be del V is equal to V post minus V pre. If it is superimposed current, del I is equal to I post minus I pre. In this case, we have taken superimposed negative sequence based impedance, and again we have taken the rate of change of, this is important, rate of change of superimposed negative sequence impedance, and so in short form ROCO SN SI. Now, if we will just see that how to take this rate of change of superimposed component in time domain, kth instant, at kth instant what is the value, this del 2, this delta z to k minus delta z to k minus 1 divided by tk minus 1. If this is a series of this particular, I mean the values of this z value, this is the delta z2, if it is delta z2. Now, we will take the rate of change means the consecutive samples, the consecutive values, this delta z2, this is at kth instant, let us say at kth instant, and this is for k minus 1, you can make it k here, this is k minus 1. This z k represents this point, and this z k minus 1 represents this point, the previous sample or previous value. Difference between these two values, that is z k minus delta z 2 k minus delta z 2 k minus 1 divided by the time, the corresponding time, this is the t axis, our delta t, I mean the difference between two consecutive values of this delta z 2, what a time gap. If we are taking this as 1 millisecond, if the sampling frequency is basically how much, it is 1 kilohertz, the corresponding delta t is going to be 1 millisecond. If it is something else, delta t is going to be varied. So, based on this recursive manner, we will just calculate the rate of change of the negative sequence based superimposed impedance. These are the steps shown: acquiring this voltage current signal at the digit terminal, and the storing the pre and post event voltage currents data which are sampled at the rate of 1 kilohertz. And next we will estimate the phasor using the WLES, means least weighted least error square based technique, and then we will calculate the pre and post event negative sequence voltage and current, and finally this Z2 pre Z2 post, and we will calculate this equation in our paper, or we have mentioned this 1213. So, here it is basically Z delta Z2 and finally the rate of change of the impedance, and if this is greater than certain threshold, then islanding is there, and if it is not, if it is below certain threshold, then there is no islanding. Yes, of course, this particular technique is also dependent on the threshold values, but however, this technique works fine for zero power mismatch condition. To realize this particular technique, we have taken one sample system like this. We have it is a 13 bus IEEE 13 bus system, where we have this PV generation, this is our PV system, and here we have another PV system, and different types of loads are also connected, here loads. So, based on this microgrid system, and here is our main grid, and the system is simulated using the RSCAD software which is present in real time digital simulator, that is RTDS. Inside RTDS we have one software that is called as RSCAD, just like our PSCAD, RSCAD, and using this RSCAD software we have simulated this IEEE 13 bus system to realize the technique. Now, if we see the first figure, here it is written SNI, that is the superimposed negative sequence impedance, right. So, SNSI stands for superimposed negative sequence impedance, and you could see that for different percentage of power mismatch, like minus 50%, 40%, minus 30%, and we went up to plus 50%. The variation is also, I mean, we did for 80%, because of course, if we exceeds, I mean, if we be close to the higher percentage of power mismatch, the factor is very good, but it is a difficult situation for lower power mismatch condition. So, in every algorithm it is desirable to test the performance of the technique for lower percentage of the power mismatch, mostly for 0 power mismatch condition. And also you can see here for 0 power mismatch condition also we have this 0% power mismatch where the technique is working properly. Now, see, for minus 50%, this is the first one is for active power mismatch, minus 50%, minus 40%, the corresponding graph is basically on the positive direction, and for the plus, that is plus 10%, 20%, 30%, the particular SNSI lie, this particular values, these values lie in the negative direction. So, this is in the positive direction altogether, and these are in the negative direction. Why? What is the reason behind it? It is a good analysis point that during this positive power mismatch condition, already we have discussed that this P load, this is our P load is greater than PDG. That means load is more and generation is less, and I am talking about for the islanded microgrid operation. At this condition, the microgrid is islanded, and we have calculated the superimposed negative sequence impedance, and then we have shown here for different percentage of power mismatch. Now, this if it is this delta P is, let us say, plus 50%, that means my PL is greater than this PDG. In that case, what happens? The V2, basically this V2 is decreased, the V2 value, because the voltage decreases, the load increases, voltage decreases, right. So, if the voltage decreases this I2, that means my Z2 value also decreases. And what happens to the Z2 pre? This is my Z2 post and this is my Z2 pre, but before this side ending the Z2 pre remains constant unless until we are going to change the system, because the system is not going to be changed anymore, the system is as it is. But during this islanded mode of operation, due to the different disconnection of the DGs or disconnection of breakers, the V2 and I2 are going to be affected, or impedance of the circuit is going to be affected. So, this Z2 post is different for different power mismatch situations. Now, if it is lower than this my Z2 pre, the difference of the superimposed negative sequence is going to be what? It will be negative, and that is why this plus 50% altogether the S and SI are in the negative direction. That means as if this Z2 post is less than my Z2 pre. And similarly, if you will come for the minus, that is a negative power mismatch situation, in that case my impedance Z2, we are expecting, assuming this Z2 post is greater than my Z2 pre, and that is why the all are in the positive direction. So, keeping in this particular concept, and we have taken this negative sequence part of this active reactive power, and this is also positive part of the reactive power, and the corresponding figure is shown here. Now, coming to the rate of change of part, why this is 0? Let us say this islanding has occurred at the 1 second, and up to 1 second, from 0 to 1 second, this SNSI, the rate of change of SNSI is 0, because before the disturbance this Z2 post is equal to Z2 pre. The difference between two consecutive impedance values, basically it is constant. That is why before the disturbance, so before the islanding, this Z2 post is equal to Z2 p, and the difference is going to be 0. And that is why this rate of change of this S and SI up to the inception of this islanding event 0. And when this island has occurred or islanding event has occurred, then there is a remarkable change in this S and SI, rate of change of the negative sequence superimposed impedance. And taking this particular change, by exploiting this particular change, we will decide whether we have to give trip command or not, whether the islanding relay is going to give some trip command or not, right. And of course, we have to see whether this rate of change of negative sequence impedance has crossed the limit or threshold value, that is also important. And in this case we have maintained 20 as the threshold value for our purpose, like for 1 kilohertz sampling frequency. If the value of this rate of change of superimposed negative sequence crosses 20, then we will declare it is an islanding event, otherwise it is non-islanding event. Also we have tested this particular technique for different types of non-islanding events, like you could see here the capacitor switching, and also different types of faults like AG fault, BG fault, and feeder disconnection here, and yes, disconnection, connection of the loads, right, inductive loads, resistive loads. So, these are all non-islanding events. The islanding event is the disconnection of the microgrid from the main grid, and disconnection or connection of the DERs within the microgrid system with the condition that the main grid is connected, those conditions known as non-islanding conditions. Capacitor switching, faults, so those are also non-islanding events. And also we have tested for these non-islanding events what will be the performance of the proposed technique. You could see here that this figure shows this rate of change of SNSI, the negative superimposed negative sequence impedance. Here the values, you could see that it crosses, it is here, this is the threshold value, this is the threshold value, and the corresponding characteristic here you can see RO, CNSI, these are the corresponding figures. Now we will go for one effect of islanding and reconnection of adjacent PV, PGU and capacitive load switching case. This is one of the non-islanding event, and here you see that for this case this is the rate of change of superimposed negative sequence current. Here you could see the value is within 20, as already I have mentioned that in case of this islanding condition, the threshold we kept 20. If the value is crossing 20, then it will be declared as islanding event, otherwise it is not. So, we have tested for different type of capacitor switching mode. Here you could see that this value is below 20, that means it is not an islanding situation. Also we have tested the performance of the proposed technique for single pole tripping situation. What is single pole tripping situation? Suppose this is one bus, this is another bus, and within this bus 3 lines are present, and the corresponding poles like of the circuit breaker are present, and due to certain fault, let us say in phase A, if any fault, AG fault occurs, the breaker of one particular, the breakers both the sides are open. That means this, if it is open and this is also open, that particular phase is out of service. We can keep it like this, it is open. So, this condition is known as single pole tripping situation, keeping other two phases healthy, other phases like B phase and C phase, they are carrying the power, whereas the phase A is faulty, so it is taken out of service. So, this condition is known as single pole tripping situation, and this situation leads to unbalancing, because one phase is out of service and it is quite good chance of generation of what the negative sequence components, and of course, the fault is there, the fault is isolated. So, this negative sequence component also may lead mislead, that it will be just say, it will say that it is an islanding situation. So, to test that, because our technique is based on the negative sequence component. So, we have to also test the performance of the technique for the single pole tripping situation, right. So, in one of the feeder we did the test, and you could see here this is the voltage and current for that particular event, single pole tripping situation. You could see here we have a fault in phase A, that is why the phase A current is almost 0 here, and this black one and this red one corresponding phase B and phase C current. And during single pole tripping there is slow oscillation which is experienced in current waveform as well as the voltage waveform due to the power mismatch, that is due to the basically the mechanical power and the electrical power. This is the corresponding SNSI, the superimposed negative sequence impedance, and this is the rate of change of SNSI. See, the value of this ROC SNSI is well within 20, because this 20 is our threshold for 1 kilohertz sampling period. See, I will also discuss in further sections that the sampling frequency also decides the threshold. If the sampling frequency is different, obviously my delta t is also going to be different. So, then my threshold is going to be changed. And this is also one of the demerit of this particular technique. If the sampling frequency varies, then the corresponding threshold is also going to be changed. And this is for sampling frequency Fs is equal to 1 kilohertz for this case. When the sampling frequency is 1 kilohertz, and for this single pole tripping situation, this is declared as a non-islanding situation. It is not declared as a islanding situation. Now, we have also tested this performance of the proposed technique for different tie line connections. For that purpose, we have taken this IEEE 34 bus system, and here you can see that different types of tie line, like tie line 1, this is our tie line 2, this is line 1, this is tie line 3. By connecting and disconnecting these tie lines, we have created 4 scenarios, like scenario 1, this is scenario 1, and this is our scenario 2, this is scenario 3, this is 2, this is 3, and also here we have scenario 4. So, based on different combination of the tie line connections or disconnections, we have decided different types of scenarios. Based on these scenarios, here we have tabulated the corresponding values of SNSI and ROC SNSI. If we will take the scenario 1, this one, so the corresponding SNSI value is 0.737 and this ROC NSI is 30.77. That means, if it is crossing 20 and it is declared as an islanding event, and you could see here throughout this table all are basically the values are above 20, and that is why all the scenarios are treated as islanding event with connection of this tie line system. That means, it indicates this tie line connection has no impact on the performance of the proposed technique. It is as good as it is declaring that this is an islanding event. And yes, we have taken here for -2% active power mismatch. This A stands for active power, P stands for power, M stands for mismatch. Similarly, also we have tested for non-islanding event for this particular IEEE 34 bus system, and here we have created a ABC type fault at F3 location and feeder 1 disconnection. These two basically taken by considering the location of different DGs like DFIG, PBPGY. This DFIG basically the wind system, and this is our PB system, and this is a synchronous based DG system. A different type of renewable sources also considered to test the performance of the technique. Now, you could see here finally, I will just come to this column where we have written this rate of change of superimposed negative sequence impedance, and you could see very clearly that all the values are below -20 or +20, right. So, that is why we can say that this particular system is very, technique is very robust even for the different type of non-aligning conditions, the technique works well. Also, we have tested for different type of control strategies which are used for the inverter of the different type of renewable sources. Let us say for our solar system or wind system, we use like PYF QIV droop control system. For the voltage source inverter, this is VSI, that is a technique used in the inverters. Now, for different types of converters, controllers, whether this technique is working fine or not. Yes, of course, because when we are designing certain islandization technique, we should test the performance of the technique for different type of control strategies, because it may happen that for certain control strategy this technique will work, or it may happen that some other technique it may not work. So, that is why it is very necessary that we should test the performance of the technique for different types of control strategies. For this case, this is the block diagram for the solar based technique, and this is a system we have simulated using this RSCAD software of the RTDS system, that is a real time digital simulator, and it is found that the technique works well, like for 10 minus 10%, 5%, 2%, this is SNSI and this is a corresponding voltage and this is SNSI, and here to some extent you could see that very close to the threshold. You know, it will be very difficult to decide whether this is an islanding system, islanding condition or not. That is also one demerit we got. It is not demerit, it is detecting the islanding situation, but it is very close. You could see here it is very close to the threshold, right. And these are for the frequency based relays, and also we have given one comparison with the existing islanding relays. Existing is frequency and rate of change of CNI both together compared, and to some extent this is also oscillatory in nature also. It is not very straightforward what we have seen in the previous results. Next, a constant PQ type control strategy which is used in VSI of the solar system also we have tested, and the total block diagram are present inside the RSCAD software of the RTDS, and here also we have tested, and this is the corresponding diagram. If you see here the rate of change of final figure, you could see here that this rate of change of superimposed sequence current, it exceeds the threshold. The threshold is 20 here and it exceeds the threshold value. Finally, I will discuss one HIL test bed, which is also very important for us to learn or to know. In our laboratory in the Department of Electrical Engineering, we have this HIL test bed facility. For this HIL stands for hardware in the loop system, and for this HIL test bed we need the RTDS real time digital simulator and DSpace 11004. Here I have just shown here, this is our RTDS and this is our DSpace DS1104, and you could see that the system, as already I have discussed, whether it is IEEE 13 bus system or IEEE 34 bus system, whatever, and these two systems are going to be simulated using this RSCAD software of the RTDS. And after this simulation we will just tap, we will take this GTAO card, means this analog output card, because RTDS has analog output and a digital output card, and also it has digital input and analog input cards. So, through this analog output card we will take the analog signal to the DSpace, and inside the DSpace our algorithm is running. The impedance superimposed, rate of change of superimposed based technique is basically coded inside this DSpace. DSpace works on the in the medium of MATLAB. So, MATLAB 13A 2013 software which is used inside it, this DSpace, that the codes are written, are embedded, and using this analog signal, the voltage current signal, it will calculate the rate of change of superimposed negative sequence impedance, and the corresponding decision is going to be fed again to the RTDS through this GTAI card. AI means analog input card. Through this it will go to the RTDS, and there the corresponding circuit breaker of the DGs or renewable energy sources are going to be opened, so that the DG will be shut down if any islanding is there. If there is no islanding, so there is no necessary to open the circuit breaker which is present near to the DGs. So, this is how this particular HIL test bed looks like, and here some of the practical pictures we have provided, and this is one of the sample result as per the hardware is concerned. You can see this is the SNSI and it crosses the threshold, that means the trip signal is going to be generated. These are some of the comparison with the conventional techniques. This is for the rate of change of power, and this is dP by dt, and rate of change of frequency and phase jump techniques. We have seen that in all the cases this NDZ is a common problem. If it is like a non-detection zone, basically zero power mismatch condition, then most of the conventional techniques fail. whereas this rate of change of negative sequence based technique basically operates. And this is also one of the technique we have also realized, negative sequence current induction based technique. This is one of the active. In of the next class I will discuss about this active island iteration based technique, there I will discuss in more detail. And this is one of the another result. And how to select this threshold also we have studied very rigorously by varying the sampling frequency 2 kilohertz, 1 kilohertz, 500 hertz, 200 hertz. For different sampling frequencies also we have simulated, and all corresponding superimposed negative sequence impedances and its corresponding rate of change of superimposed negative sequence impedance also we have calculated, and we found that based on this varying this sampling frequency, the threshold also varies. That is one of the demerit of this particular technique. And this is how this percentage of active power mismatch and the time, and this is the PV generation capacity and the corresponding parameter, that is rate of change of SNSI varies. Now, in summary I will just discuss here that a solution we have provided here based on the superimposed negative sequence components, and the harmonic if present inside the voltage current signal. By using a least error square based technique, we can always extract the fundamental voltage frequency phasors. And in this case we have taken one IEEE 13 bus system, and also we have simulated one IEEE 34 bus system, where we have also taken the tie line switches and single pole tripping situation, high impedance faults, different islanding and non islanding situations are created, and the corresponding results are basically tabulated, and it is also figured out. And it is the final conclusion for this particular technique is it needs rigorous simulation practice by varying the sampling frequency, how to set the corresponding threshold. That is one of the major drawback of this particular technique. Thank you to all of you.